use the integral test here to show that some series either converge or diverge. So we're going to be looking for things. This is a good test to apply to series where the corresponding integral is something that's easy to evaluate. So classic case here is going to be the harmonic series. So the sum from n from 1 to infinity of 1 over n. So this is a very famous and well-studied series. Starts off 1/2, 1 plus 1/2, plus 1/3, plus 1/4, so on and so forth. So let's just observe here, it's a series with positive terms. They are getting smaller and smaller and smaller. The limit of the terms is going to 0, so this may or may not converge right now. So let's think about what's going on here. The appropriate function we want to think about is f of x is 1 over x, because a sub n is equal to f sub n for all positive integers n. So now we want to go to the integral test. F is a positive, decreasing, continuous function. This is positive, this is decreasing, this is continuous. So now we want to ask ourselves, what is the integral from 1 to infinity of 1 over x dx? We could, this is something you should recognize. I'll just do it from scratch. Limit as r goes to infinity, and then you go from 1 to r, 1 over x dx. The limit as r goes to infinity of natural log of r minus natural log of 1. And this limit as r goes to infinity, log of r goes to infinity. And so this is infinity. And so what do we conclude? This diverges. So we integrate the corresponding function. 1 over x corresponds to 1 over n. That satisfies its positive, decreasing, and continuous. And so, because the corresponding integral diverges, then the original series diverges. That's how you use the integral test. So that's a very classic example, and we'll come back to this in the near future. Let's do another example here. The sum from n from 1 to infinity at n divided by n squared plus 1, n squared plus 1, all of that squared. And so, once again, we're going to write down the corresponding function. F of x is x over x squared plus 1, quantity squared. So let's go ahead and check. It is clearly positive. It's clearly continuous. It's a rational function. Rational functions are continuous as long as they're defined, and this is going to be defined everywhere. And so then just to think about whether it's increasing or decreasing, we'd have to check the derivative. So a little bit of crunching here says that f prime of x is 1 minus 3x squared over x squared plus 1 squared. And a little bit of thought here says this is always positive. The denominator is always positive. And 3x squared is going to be bigger than 1. So 3x squared is going to be bigger than 1 as long as x is greater than or equal to 1. So this says it's decreasing because the derivative here is negative. So okay, great. The integral test is going to apply here. We have a positive decreasing continuous function, and it's decreasing if x is at least 1. It's not necessarily decreasing if x is less than 1, but we don't care about that. So let's do the integral. So the integral from 1 to infinity of x divided by x squared plus 1, quantity squared dx. So the limit as r goes to infinity of integral from 1 to r, x over x squared plus 1 squared. And so now we're going to want to find the antiderivative, and you're paying attention, this is great for substitution. U is equal to x squared plus 1, du is equal to 2x dx, du over 2 is x dx, because we've got a factor of x dx sitting right there. So our life is great. Limit as r goes to infinity of So 1/2 du divided by u squared. And our bounds change from when x is 1, u is 1 plus 1 is 2. When x is r, it's r squared plus 1. And so now we integrate, limit as r goes to infinity, of 1/2 times minus 1 over u, and we plug in 2 and r squared plus 1. And so limit as r goes to infinity of minus 1/2 times 1 over r squared plus 1, and plus, sorry, that should be a minus 1 over 2. Okay, so as r goes to infinity, this whole fraction goes to 0, and so we're just left with minus 1/2 times minus 1/2 is 1/4. So because this converges, because the corresponding integral converges, that tells us that the original sum also converges. But importantly, note, this does not tell us that the answer here is 1/4. We can't just say that this series is equal to 1/4. It just tells us that this converges by the integral test. So once again, in this chapter, we're not really trying to figure out exactly what this series is equal to. Our only goal is to figure out, is it